This presentation is for the course COT 5405, Design and Analysis of Algorithms. So today's presentation topic is lower bound proof of element distinctness problem. The roadmap for today's problem is, first of all, we'll introduce the element distinctness problem, then we'll show why sorting lower bound method doesn't work for EDP, and then we'll prove that the lower bound for EDP is omega of n log n. Element distinctness problem. So we have input is an array A containing n elements. The computational model that we are going to use is comparison, and on comparison, each number with each will come up to an output. So the output will be yes if all AIs are distinct, and no if for some I comma j AI is equal to AJ. So example. So as you see in the first example, the input array A contains every distinct elements, so the output is yes. In the second example, 7 is repeated, so the output is no. In the third example, you can see there are multiple repetitions, 7, 2, so still the output will be no. Sorting lower bound method. So we have a theorem which says for any comparison-based sorting algorithm must take omega of n log n time. For this, we'll talk something about the decision trees. So decision tree has a leaf node, non-leaf node, leaf edges. So leaf nodes, it will contain the possible permutations. Non-leaf nodes will be where contain I column j, and the leaf edges will contain comparison-based, will contain relational operators. And the execution always begins at the root, not level I comma j. AI will be compared with AJ, and the execution will follow accordingly, branch appropriate leaf, and whenever execution arrives at any leaf, its label will be the output. Let's assume an array of size 3. So our input size is n equals to 3. So we'll get a decision tree, something like this, equivalent to this. So each number of possible answers or number of possible permutations, in our case, it will be n factorial weights. So since we have n equals to 3, so number of leaf nodes will be equivalent to 3 factorial, which is equal to 6 leaf nodes. 1, 2, 3, 4, 5, 6. So the conclusion that we're going to take from this one, from this decision tree, is that each leaf node that we see is a permutation of the input array A of size 3. So the number of possible answers is equivalent to now n factorial, that is the total number of leaf nodes. So for a normal sorting problem, with the input is array A containing n elements, and output we are going to give a sorted array A. So the proof is that the possible answers, the way we are going to negate a sorted array is n factorial. That is each possible permutation of A, which we talked about in the previous slide. So the program tree must have at least n factorial leaves. Its time taken is equivalent to the height of tree, which is equal to log n factorial, which is equivalent to n omega of n log n. But this case will not work in our problem. EDP has only 2 answers: yes if all elements are distinct, or no if duplicates exist. So lower bound will be log of 2 equals to 1, which is a very silly bound for the EDP problem. So we'll try to come up with a new method, and to solve that the time complexity for EDP is omega of n log n. So today's major focus is on this part. So the abstract on how we are going to prove is that, first of all, we are going to utilize n-dimensional geometry to interpret input array, our input array A, as a point in an n-dimensional space. What does that mean is that the points that we see, so A1, A2, A3, A1 will represent the first coordinate, A2 will represent the second coordinate, AN will represent the nth coordinate, and the entire thing, that is A, array A, represents a point in an n-dimensional space. We are going to restrict the instances to the unit n cube. We'll talk about this later on. And then we'll use the notation of R of L, which stands for the region of L. The region of L is all the set of all the instances where leaf L is reached upon execution. We will assert that R of L is connected. Then we'll go with another claim. We'll assume that A, our input array A of n consists of n distinct elements. Then we'll take an array B, be a non-trivial permutation of A, and then we are going to show that A and B must reach distinct S leaves. Then we are going to show that there must be at least n factorial leaves, all giving yes answers. That is, S leaves is greater or equals to n factorial. Finally, we'll conclude that the tree must have at least n factorial leaves. So the time complexity we'll obtain is that T of n will be equal to height of 3 equals to log of n factorial equals to omega of n log n. So first of all, we understand the n-dimensional space. The framework will interpret your input array as a point in an n-dimensional space. We will be restricting the instances to unit n cube. That is, all the AIs will lie between 0 and 1. For our simplicity, we will visualize an n-dimensional space into a two-dimensional space. For our instance, first coordinate is A1, second coordinate is A2. So this is our A1 axis, this is our A2 axis. So the unit cube in 2 dimension, this is a unit cube in 2 dimension. So the thing that we are going to see is that whenever A1 is on this line, the diagonal line, these are all the instances where A1 is equal to A2. So these instances will give us a no instance, whereas the remaining, this triangle and this triangle will give us an S instances. So what we have done in this here is that we have taken our problem, we have visualized it in a two-dimensional space. So now after interpreting this sequence, we have a claim. We have claimed that R of L, the region of L, is connected. We'll prove this. Before we show this, we have to understand what does a connected region means. So a connected region, a region R is said to be connected if for any points A comma B belonging to R, there exists a path from A comma B entirely passing through R. Now we'll introduce a concept called convex region, which we are going to use to prove that RL is connected. So convex region, a region R is said to be convex. For any points A comma B belonging to R, the straight line path from A comma B passes entirely through R. We will see that convexity says that convexity implies connectivity. This is the main thing. The reason we are saying, see, the connected region, we say that there exists a path from A to B entirely passing through R, but we make our algorithm more distinct or more spatial. And we say that the straight line path from A comma B passes entirely through R is said to be a convex region. Ultimately, we are, since the convexity is simpler to prove, so we'll be working on the convex. We'll prove that RL is convex, so thus RL is connected. Hence, convexity implies connectivity. So the few examples of convex objects are cube, sphere, and few examples of which are connected but not convex, like kidney-shaped or torus-shaped object. So now will prove our first claim, RL is connected. So let A and B be 2 points in RL. So I will consider 3 executions. So in execution 1, the instance is A. So by definition, L reached. Instance execution 2, instance equals to B. So by the definition, L is reached. In execution 3, will take different, little bit twisted of instance. The instance equals to C, where we'll consider a point C equivalent to this, and we'll define it as Ci is delta times AI plus 1 minus delta times Bi for all I, and we'll restrict delta to unit, where delta lies between 0 and 1. So if delta equals to 0, Ci is equals to Bi, because all AI component goes away. If delta equals to 1, all Bi components goes away, and Ci is equals to AI. If delta equals to 0.5, then Ci will be half of AI plus half of Bi, which is ultimately will give us a midpoint of line segment A, B. So we are designing C such that it happens to be on the straight line AB. So now we'll prove. So remember that our decision tree, so root level always has I column J. So we'll suppose that less than branch is taken in execution 1. So in execution 1, less than branch is taken, which means less than branch will be taken in execution 2 also. Since we have already seen this one, and we know that AI is less than AJ, BI is less than BJ. Now in this inequality, we'll add the delta component. So delta times AI plus 1 minus delta times BI will be less than delta times AJ plus 1 minus delta times BJ. If we see this one corresponds to this form, so this will be equivalent to CI less than CJ. So which means that less than branch is taken in execution 3. Similarly, other branches reaching L will find other branches reaching. Similarly, in this manner, other branches will reach L finally. So we can say R of L is convex, which implies R of L is connected. Claim 2, let A equals to consist of distinct elements, and let B be a non-trivial permutation of A, then A and B must reach distinct S leaves. So we have been given A consists of distinct values, which means answer of A should be S. And B is some non-trivial permutation of A. And since A has distinct elements, means B also will have distinct elements. So answer of B will be S. So the way we are going to prove this claim is by proof by contradiction. So for the proof, we'll assume that A and B, which is same leaf L. And we already know that we have already defined the component RL. RL are the instances where L is reached upon execution. So from our previous claim, we know that RL is connected, which means there exists a path P from A to B entirely through L. Now we will show that there exists coordinate C in the path P, which gives us answer no. So the basic subclaim to uphold our statement will say that there exists I comma j such that AI is less than AJ where BI is greater than BJ. Let's define a function fx, which is simply gives us the difference of the two coordinates xi minus xj. So when we apply this function to the input array A, we see that AI minus AJ will always be less than 0. And we'll apply to this function B, we'll see that f of B will always be greater than 0. Since it is a continuous function, my mean value theorem will get that there exists a point C in path P such that f of C is equal to 0, which means f of C equals to 0 means that Ci minus Cj equals to 0, which means Ci equals to C0, means these two elements are not distinct. C leads to a no leaf. So answer of C equals to no, which is a contradiction. Hence, we can, by contradiction, we prove that containing sub and distinct A and B must reach distinct as leaves. So further proof of the subclaim will be proved by example. Our subclaim is that there exists I comma j such that ai is less than xj while bi is greater than bj. For this, let's consider an example. So we have an input array A with these elements. We have input array B with the elements with these elements. And let S of A be the sorted array. So S of A is equals to 13, 17, 25, 37, 98, and the decision tree will get in this is and the index will start from 1, 2, 3, 4, 5, 6. So decision tree index is 2. First of all, 13. So 2, 3, 1, 5, 4, 6. And S of B is what? B is a non-trivial permutation of A. So we just arrange this. So S of B will arrange B. S of B will be a non-trivial permutation of S of A. And we'll follow the decision tree method. So for 13, 17, 13 will be followed by 17, 17 will be followed by 25, and so on. So we know that A and B are distinct. Since A is distinct and B is a non-trivial permutation of A, so B is also distinct. So when we sort A, there exists I comma j pair such that I is less than j. That S of AI is always will be less than S of AJ. See? These things are in sorting, increasing order, so it will always be less than. At some point, we'll notice that B should be non-increasing. That is, B, which is the initial permutation, will not be sorted. Means that there exists I comma j such that I is less than j. S of Bi will be less than S of Bj. See? This part. Sorry, this should be greater than S of Bj. Bi is greater than S of Bj. So what we see is that, and now we'll map the I comma j back to A comma B, and finally we'll conclude that there is this point I comma j such that A is less than AJ while Bi is greater than Bj. After proving our main two claims, so we finally arrived to claim number 3. So we see that every distinct permutation, which is a different region that we proved in the previous case. So the number of distincts, we know that now we know that number of distinct permutation can be n factorial. Therefore, number of S leaves must be bigger than n factorial. That is, number of S leaves is bigger than n factorial. The natural measure of complexity is the height of the tree, which corresponds to the worst case number of comparisons for inputs of size n. The tree must have at least n factorial loops. The time taken is equals to height of tree is equals to log n factorial. Therefore, T of n equals to omega. Finally, we come to the proof for the EDP.